Hello everyone. Sorry I can't be with you today. I thought I'd put a little video together just to make sure we keep moving since we missed a couple of periods on Friday and then another one today. And I know how busy you guys are, and we're starting to move through material at a reasonable pace. So I apologize for the budget bob setup here, and it's pouring with rain outside, but look, we'll see what we can do today and try and see if we can help you fill in at least some of the pages in your booklet. So what I want to look at today in this particular video is the nature of acids and bases. So the first thing we need to do then is to have a look at a few different definitions. The first thing will be that an acid is a chemical substance which can donate a proton. Now, we have already looked at this in the past. We've already made fairly clear that we understand the concept of a proton donor, and so that's part of what we're trying to do here, is just make sure that you are starting to shift your understanding of acids and bases into the concept of proton donors and proton acceptors. Secondly, that a proton is a hydrogen ion. So we talked last week about the fact that the hydrogen atom has one electron and one proton, and so in the nucleus of the atom, when you have just the one proton left and the electron has gone, then all you have left is a proton, and so that's where that particular definition comes from. So when an acid solution is prepared, the acid molecule ionizes by donating a proton to a water molecule, leaving the anion. So in this case, what we have is, and if I put H, excuse me for the fairly coarse way, I'm still getting used to this little pad. So if we put HA as being a general formula for any acid, then what we have is an H plus and an OH minus. An A minus, which will be the anion that's left over after the acid has ionized. So when we look at how this reaction works specifically in relation to a water molecule, then in terms of its proton donation, HA in aqueous plus H2O. I'll leave the subscripts out at the moment because I can't write them particularly well. So we will get H3O plus and A minus. And this is where the H plus, the proton, has actually added to the water molecule and given us the hydronium ion. So the hydrated proton is called a hydronium ion. We have had a look at that before, and I guess that's something that we probably are reasonably familiar with. But this is a very important ion, and so it's very important that you understand how that forms and why it is important in acid solutions. So, little activity for you if you haven't already done this, and excuse me for disappearing for a second, but there are some pages in your book which you might want to go through and double check that you've completed at this stage. And I should have had it in front of me, but I don't. But the section from page 41 onwards is where all of this begins. So you can sort of follow along with some of what we're doing in this particular PowerPoint from pages 41 to 42. So I've got a couple of examples of the ionizations that I put there. So here's the first one. Can you complete this ionization? So obviously what we want to do here is we just want to make sure that we are putting in the hydronium ion, the H3O plus, and the Cl minus. In the second one, we have nitric acid. So again, you're going to make sure that you put the hydronium ion in. That's always the first thing you do for acids, because that's the proton that's attached itself to the water molecule. And then we look at what we have left over, and that's our anion, which in this case is an NO3-. In the third situation, we have a diprotic acid. This particular one, sulfuric acid, is diprotic because di means two. So it will be able to donate 2 protons. So therefore, we will need 2 water molecules. We'll end up with 2 H3O plus ions and the SO for 2 minus. Oops, for 2 minus ion. So what we also need to do is to have a little bit of a look at organic acids. And there's a couple of important ones that you need to know about, and we have briefly talked about these before, but I thought it would be worth just going through them again now. So firstly, organic acids are organic compounds with acidic properties. That probably makes sense to you. And we've looked at a small number of organic compounds so far. So organic compounds, when we're talking about organic compounds, we're basically talking about compounds with a carbon skeleton. They're usually characterized by the COOH functional group. So in this case, what we're looking at is the C double bonded to an oxygen and then single bonded to another oxygen, which is bonded to a hydrogen. This is the functional group for all organic acids. So that's the group that you're looking for in order to determine whether or not you have an organic acid functional group. Now, most of the organic acids are weak acids, and therefore they will not fully ionize, and I will produce one more slideshow for you which will look specifically at the difference between the strength and the concentration as we apply those terms to acids and bases. So the two examples we want to look at are acetic acid and citric acid. So the first of these is acetic acid. And acetic acid is one we've talked about before. Acetic acid is also known as ethanoic acid, and that ethanoic acid is what tells you about a way of drawing this particular compound. So this is the information that we have. Eth means 2, so we know there are two carbons in this compound, and then the anoic acid ending is what tells us that it's an acid, and so that means it will have the COOH group. Acetic acid is a major component of vinegar, but not only that, acetic acid can form from the fermentation of fruits such as grapes. So acetic acid is actually a big problem in the wine industry. We have a lot of the whole process of fermentation is to turn the glucose sugars or the fructose sugars into ethanol, alcohol. The problem with ethanol is it can readily oxidize, and there's oxygen everywhere, into acetic acid or ethanoic acid, and that changes, obviously it will change the taste. If wine's been left open for too long, then it can oxidize, and so the flavor of the wine starts to become more sour, and that's due to an increase in the concentration of the ethanoic acid, and we know that acids have a sour taste. There's a form of acetic acid called glacial acetic acid, and glacial acetic acid is the most concentrated form that we can have for acetic acid, and it has a molarity of 17 moles per litre. So, structure of acetic acid. Well, if we want to draw the structure of acetic acid, then what we're going to need to do is to use the name ethanoic acid in order to do that. So, we know that F means 2. So we draw 2 carbons in. We know because it's an acid group that there's going to be 1 carbon that's going to be bonded to an O and another one that's going to be bonded to an OH. And then all we do is to fill in the rest of the bonds that are needed with hydrogens. And hydrogen. So this is the structure of acetic acid, and I'm sure you can do a slightly neater version of that than I can on this little pad. What happens when acetic acid is ionized? Well, when acetic acid is ionized, what we need to do is we need to work out the formula. So from what I have drawn above, you can see the formula is CH3COOH, and it's probably not a bad idea to write it in this form. Oops. Aqueous. When it is added to water, liquid, because it is an acid, it will ionize in the water. But I'm going to draw an equilibrium arrow here because this being a weak acid will not fully ionize. Because it's an acid, we always get a hydronium ion, so H3O+, but we will also get the anion. In this case, CH3, the hydrogen that has become part of the donated one comes from the acid functional group here. This is the hydrogen that becomes a proton and disappears. And as it disappears, you get left with a negative charge on that particular oxygen. So both of these species would be aqueous. It seems to muck up whenever I try and write aqueous. There we are. And this is an acetate. Yep. Acetate. Let's not try and write. Acetate or ethanoate. So without the IC, with an ATE ending, that will be the salt. So if it was being reacted with something like sodium chloride, sodium hydroxide, then we get water forming and we would get sodium acetate. That's the way that the naming system would work. The other one we'll have a look at in just a little bit of detail is citric acid. Now, citric acid is a triprotic acid. So that means it has 3 of the acid groups, and its complex IUPAC name is 2-hydroxypropane 1,2,3-tricarboxylic acid, and I briefly drew that for you last week. Citric acid can be found in citrus fruits such as lemons, oranges, limes, those sorts of things, and it's often used as a food additive because it can add, because it's an acid, it'll add sourness, but also because it's an acid, it changes the pH and therefore can actually inhibit the growth of particular microorganisms such as mold. The structure of citric acid, and this is going to be a real major pain to try and draw in the space that I have, but if you remember, the propane is the first part, hydroxy is the OH group, and that comes off the number 2 carbon because it's 2 hydroxy. And then the 1, 2, 3 means off the 1, 2, 3 we have the acid groups. Okay, make sure that you do these yourself because this is very messy and it's probably not going to be easy to see. And then again, what you do is you just make sure that you make every carbon up to 4 bonds. Oxygen will have 2, hydrogens will have 1, and the carbons will have 4. So with these ones, 1, 2, 3, 4, that's okay. 1, 1, 1, 2, 3, 4, that's okay. Down here, 1, 2, 3, 4, they're okay as well. So this mess here is citric acid. Then the ionization of citric acid. So if we want to do the ionization of citric acid, this is going to be a real nuisance. So what we want to try and do is to group the bits and pieces together. So we've got C3, H4, or maybe even H5O, and then in brackets will be COOH 3 times. And again, if we can separate out the COOH, that's telling us where the acid group is. And so if we then add it to, we'll need 3 water molecules. Again, because it's an organic acid, we'll use the equilibrium arrow, and we're going to have 3 hydronium ions, H3O+, and then the C3H5O and COO3 minus. Okay, that's pretty much all for this one. I have put a second video on which will be a little bit more of an extension, specifically looking at the difference between concentration and strength for acids. And there'll be a couple of examples of questions there. So once you're happy with this video, you can stop it and have a look at the next one.